Our today's speaker is Bernhard Reinke from CNRS and Sorbonne. So he will tell us about transcendental dynamics and iterated monodromy groups. So please start.
Okay, thanks, Kostya, for the introduction, and it's a pleasure to be able to speak here, even though it's just virtually. So today I want to talk about transcendental dynamics and iterated monodromy groups. And so first of all, this is part of holomorphic dynamics. I hope most of you are familiar with holomorphic dynamics, but just to get this over quickly, we are studying holomorphic functions under iterations. And so one thing which is very well known is that holomorphic functions can be used as a source for fractals, i.e. self-similar sets. And so what I want to talk about today is some other kind of self-similarity. But first of all, what kinds of holomorphic functions am I interested in this talk? We are only interested in entire transcendental functions. So there are four main classes of holomorphic functions which you would like to iterate, and you can distinguish them whether they have finite degree or infinite degree, or whether they're entire or non-entire. And so what I will be focusing on is only the entire part. And so what I want to emphasize is the similarities and differences between polynomials and entire transcendental maps. And so here the function 1 minus z times the exponential function will be a guiding example throughout the talk. So I will use this function most of the time whenever I'm talking about a specific entire transcendental function. And so what I'm interested in is not really forward iterating of points, but looking at backwards orbits. So if I have an entire function f and I have a point t, I can also not only look at its forward orbit, but I can look at its pre-images. And so the central question or the central slogan, one could say, I want to address is, how do pre-images move if I move my point t? So if I move my point t and come back to it, what happens with the pre-images and what happens with the iterated pre-images? And so one way to formalize this is using the iterated monodromy groups. So the ways how you can permute the pre-images are encoded by the iterated monodromy group. And so iterated monodromy groups are examples of self-similar groups. So I won't define this precisely, but I want to motivate the study of self-similar groups. Namely, they have often very exotic properties. So the first example of a group of intermediate growth, so this is the famous Guillotot group, is an example of a self-similar group. And also iterated monodromy groups of polynomials have interesting properties with respect to amenability. So the Basilica group, so the IMG of the Basilica map was the first example of an amenable group which is non-sub-exponentially elementary amenable. And so what I did in my thesis and further research is the study of iterated monodromy groups. And so the main result I want to address is the following. So if you have a post-singularly finite entire function, then the iterated monodromy group is amenable if and only if its monodromy group is amenable. So this answers exactly when the iterated monodromy group of an entire function is amenable. I will define amenability later on in the talk, but so this is one of the main key phrases you can keep in mind as a main result. So what's the plan for today? I will first go a little bit back and talk about monodromy. So in order to prepare us for iterated monodromy, and so then in the iterated monodromy groups. And then I will sketch self-similar groups. So these are linked with groups defined by Automata, and I will tell you how we can interpret the iterated monodromy groups as self-similar groups of a specific kind. And finally, I will say something about amenability and sketch how we can prove the result. And then I have some concluding remarks, and if time permits, we can branch off into some other subtopics. So first of all, from monodromy, I first want to briefly recall a little bit of function theory. So I think most of you are familiar with this. So if I have an entire function, then it can have a critical value. So that's the value of a critical point. A critical point has derivative 0. Or we can also have an asymptotic value. So this is the limiting value of a path that goes off to infinity. The most famous asymptotic value is 0 of the exponential function. If you take any path whose real value goes to minus infinity, if you apply the exponential function on it, you will converge to 0. So 0 is an asymptotic value of the exponential function. And so in my talk, I define the singular values as the union of critical values and asymptotic values. In principle, you might also want to consider the closure of it, but we will soon see that I will only consider finite sets. So whether you take the closure or not is not too important for me. And so we have some examples. Okay, I already mentioned the example of the exponential function, but for the quadratic family z squared plus c, we know that the only critical value is 0. And so for my favorite example for this talk, 1 minus c times the exponential function, it's easy to calculate that 1 is a critical value because 0 is the critical point of this map and maps to 1. And also that 0 is still an asymptotic value, also basically by the same path going off to minus infinity. So it's very similar to the exponential case. So we have 1 asymptotic value and 1 critical value for this function. And so why am I interested in singular values? So there's a classical theorem that if you have an entire function, then you can consider this as an unbranched covering away from the singular set. So you have an unbranched covering from C without the preimage of the singular set to C without the singular set. And in particular, what's interesting for me is that you can use unbranched coverings to lift paths. For example, if I take a path which goes once around 0, and I take the preimages under the map z squared, then I can lift this to a path. But so something which happens is that if I start with a loop, I don't necessarily have to end up with a loop. So if I start at this preimage of that point here, and I take the preimage of the loop, I land at another preimage of the loop. And so this will be the monodromy action which we are interested in. And so similarly, in the exponential case, if you take one loop around 0, then if you take the preimages, this will be just put into a vertical path. So if you have a preimage, then the loop lifts and comes back to a preimage with its 2 pi I higher. And so we can be a little bit more precise. So from now on, I will only consider the Spicer class. So these are functions that have, these are transcendental entire functions with only finitely many singular values. And so the thing I just described gives us an action of the fundamental group of C without the singular set on the preimages of the base point. And so first of all, let's fix a nice generating set for the fundamental group. So how are we doing this? So something I like to do, and this is again in the example of 1 minus z times the exponential function, you take paths up to infinity that don't cross as starting off at every finite singular value. And so here, for example, we can just take a part of the real lines. These obviously don't cross. And what we are doing now is we take the loops that cross one of these paths exactly once. So these paths are called spider legs. And so the Rose graph is dual to spider. So every path in the Rose graph crosses one spider leg exactly once in a positively oriented way. And if we have something like this, then we can take the preimage on our entire function. So in this case, 1 minus z times the exponential function. And we arrive at something like this. And from this, we can view the action of the fundamental group. For example, if I look at the action of this element G, I take a preimage and send it to the ending point of the lift of G. So for example, this point would be fixed, but each of these points would be sent up. And similarly, for this generator H, my action does the following. It interchanges those 2 points and fixes all the other points. And so since I know how my action works on generators, I can use this to deduce the action of the full group. So one advantage of using Rose graphs is that there's a very nice correspondence between orbits of the generators of the Rose graphs and preimages of the singular set. So for example, I have here, if I take a lift of the generator H, I have a 2 cycle here. And so this is a 2 cycle which has 0 inside of it. And so this corresponds to the fact that 0 is a critical point mapping to 1. So finite non-trivial orbits correspond to critical points. We have also a bunch of regular preimages of 1, and these correspond to trivial orbits where the Rose graph generators do nothing. And if I have an infinite orbit of a generator, so here, if I take the lifts of G, I have here an infinite orbit. And so this corresponds to the fact that we have a logarithmic singularity over 0 on the left half plane. And so for this, it's very convenient to use these Rose graph generators because we have this correspondence. And with this in mind, we can try to define some kind of combinatorial description of how we expect these preimages to look like. So this is now a little bit general, but the main example will be the picture we have just seen before. So if I have any set X and I have a family of permutations, I can construct a cycle diagram, and it's built of as follows. So the vertices, so the zero skeleton is just the set X. And so for every generator, I add in edges from a point to its image on the permutation for each permutation. So if I do this with the setting we had just before, I arrived at this picture. And this is also called, so I call this on the setting when, and I think in general you should only do this when it's connected. But so I call this the Schreier graph of family of permutations. And so now I want to glue in some 2 cells. And how do I do this? I glue in 2 cells along every finite orbit. So here I have a trivial orbit, so I glue in a 2 cell. Here I have an orbit of length 2, and I glue in a 2 cell, and I glue also in a 2 cell for every trivial orbit along this line. And so now I can define the following. So I say that the family of permutations is a dendroid set of permutations if this CV complex is contractible. And so I should say that for finite sets, this notion is already due to Nikischevich, and I extended this to infinite sets as well. And what is our motivation for this is the following lemma. So if you have an entire function in the Spicer class, and you take a rows graph generating set, then the rows graph generators form a dendroid set of permutations. And it's not hard to see the proof idea in this picture in the case of our favorite example. So the thing which you could try, you know that C is contractible. And so what you could try is to contract C onto the cycle diagram. And for this, we have here this white component where it's not too hard, which is in principle the preimage of this white component. And it's not hard to see that you can contract this onto its boundary. And another thing which we have to contract is basically the logarithmic singularities. And so you can also contract this region onto the boundary of the circle cycle diagram. And so with this, you contracted all of C onto the cycle diagram. And as C is contractible, this also means that the cycle diagram is contractible. So with this in mind, and now I can go over to the part of where we're actually doing dynamics, or are there already some questions concerning the monodromy part? So if not, then I would, yes?
No.
Ah, okay.
Go on.
So in order to define iterated monodromy groups, I first want to specify the class of functions which we are considering. And so I'm only considering post-singularly finite maps. So the post-singular set is the forward orbit of the singular set with 0 iteration included. And I say that entire function is post-singularly finite if the post-singular set is finite. And again, here we don't have to worry about closure because we are only considering finite sets. And so the basic facts that I'm going to use is the post-singular set is forward invariant. And for every iterate of f, the singular set of the iterate is contained in the post-singular set. So with the lemma that we have seen before for unbranched coverings, we can apply this to every iterate. And since the singular set of the iterate is contained in the post-singular set, we know that for every iterate restricts to an unbranched covering over C without the post-singular set. And in particular, this means if I take a base point in C without the post-singular set, then the fundamental group of C without the post-singular set acts on the set of n-level preimages via monodromy of the nth iterate. And we can do this all together at the same time. And one way to organize this is by using the dynamical preimage tree. So what is the dynamical preimage tree? If I take, again, a post-singular finite entire function, and I take, again, a base point away from the post-singular set, then as vertices of my tree, I take the formal union of all preimages. And so what I mean by this is that I take a disjoint union, for example, if f is a fixed point, if t is a fixed point, then it will appear again at every level as an additional point. And so how do I connect points in this tree? I just take a point and map it to its, connect it to its image. So of course, if I start with the base point t, then on the first level, everything is connected to the base point. But so for the second level, we have to decide to which first preimage we want to map. So then it branches out. And so if I take a polynomial, then the nth level of this tree has d to the n vertices, where d is the degree of the polynomial. But for a post-singular finite entire transcendental function, every point has outside the post-singular set has always infinitely many preimages. So every vertex here will have infinitely many children in the case of transcendental maps. And now the fundamental group of C without the post-singular set acts on every level via monodromy. And this is then altogether the iterated monodromy action. And so something I should say is that this action preserves the tree structure. And why is this? So if I have a preimage of t here, and let's say I have some path here, so I have some path gamma here, and I look at the preimage, for example, and it takes this preimage to this preimage, then I know if I take another preimage of this path, it will send a preimage of this point to a preimage of this point. And so with this in mind, we're actually preserving the tree structure. Okay. So I think if I since I did this on Zoom, I should clean this up. This is what I was just saying. The iterated monodromy action is actually an action of tree automorphism, of rooted tree automorphisms. And with this, we now can define the iterated monodromy group. So if I act via tree automorphisms, I have a group homomorphisms from the fundamental group of C without the posterior set to the set of automorphisms of this tree. And I can define the iterated monodromy group either as the image of this group, so as a subgroup of automorphism of the dynamical pre-image, or via the first isomorphism theorem, can also think of this as a quotient of the fundamental group of C without the posterior set by the kernel of this map. And so this is one way to define the iterated monodromy group. And now we can state some properties of iterated monodromy groups. So it's well known. So this is due to Bartoli, Kamanovic, and Nikashevich, that if you have a posterior finite polynomial, then the iterated monodromy group is always amenable. And so the way they've shown this is to show that these groups are actually groups generated by bounded activity automata on finite alphabets. And these groups are always amenable. So this is what I have shown. And so my proof strategy for the main result that the iterated monodromy group of posting a finite entire transcendental function is amenable if and only if its monodromy group is amenable goes along a similar way. We want to realize the iterated monodromy groups of entire functions as bounded activity automata on now infinite alphabets. So we do this by first saying a little bit about what I mean by automata and bounded activity automata. So what's an automaton for me? An automaton is for me just a map from q cross x to x cross q, where q I call state set and x I call the alphabet. And so for me, the state set we will assume to be finite, but the alphabet will for us be most of the time infinite. And so things which you should have in mind is that q roughly corresponds to the posterior set, and x roughly corresponds to the pre-images of some base point. And so I use this notation. So if my function sends the point, the pair a comma x to something, I call the first component of this part a applied to x, and the second part a restricted at x. And here's an example of how you can visualize automata. So there are two ways which are very natural for us. So there are Moor diagrams. So for the Moor diagram, you have for every state a vertex. And so you have an edge from a state. And so you can basically see at this edge that A applied at 1 is 0, and A restricted at 1 is A. So the restriction is the image point, and so map can be viewed off by the second component here. So this would mean that A sends 1 to 0 and restricts to itself if it sees 1, and if it sees a 0, it sends the 0 to 1, but it restricts to E, and E is the state which is very boring. It takes some letter and puts this letter out and restricts to itself. So this is something which we call an identity state. And another way, which I will use more often, is basically to do something dual to this picture. So this is called the dual Moor diagram. So for this, I basically interchange the roles of Q and X. So now I have one node for every letter, and I have a family of colors for every state. And I label, if I want to know, for example, what is A applied to 0, I just have to follow the red edge. And if I want to know what the restriction of A at 0 is, I just have to read off this letter here. So again, these two diagrams encode the same information. And what we can do with Automata is we can not only consider them as the map from Q cross X to X cross Q, but we can extend this to a map from Q cross X star. So these are the sets of words in X to X star cross Q. And so what are we doing? We are basically pushing through state using these transformation rules. So for example, here I apply A to 1. So I follow this. So this means that I have to replace the 1 by a 0. And because this label here is A, I keep the letter A. Now I apply A at 0. And this means I change the 0 to 1. But now I become the state E. And then I apply the state E to 0. And this means I follow this loop and don't change the 0. And at the end, I spit out an E. So this is the way how to extend this and reading off the extension via this diagram. And so we will see this diagram a little bit more often, but also this kind of diagram will be convenient. So with this in mind, this is a very general definition, but I'm interested in groups. So for this, I want to define what a group automaton is. So a group automaton is an automaton where if I forget the second component, then we have a family of permutations. And I also, for technical reasons, I want to assume that I have an identity state which does nothing interesting. So it keeps the letter as it is and always restricts to itself. And if I have this, then it's not hard to see that actually under this extension, we also always stay a bijection. So I can use this group automaton to define a group action of the free group generated by letters in Q on the standard X regular tree. Okay, what is the standard X regular tree? Here I drawn an example for the alphabet 01. As vertices, you have letters. As vertices, you have words in your alphabet, and you get a child by appending one letter to it. So you start off with the empty word, then you append 0 to the empty word, so you just have 0. Then you could, for example, append 1, and you have the word 0, 1. And it's not hard to check that if you have a group automaton, then this defines an action on the standard X regular tree. And these are the main examples of self-similar groups. So the general definition of self-similar groups is a little bit more general, but for us, if you think about a general, if you think about a self-similar group, you should have a group which is generated by some kind of group automaton. And now I can also, with this definition, tell you what bounded activity means. So bounded activity tells you something about the possible non-trivial restrictions. So I say that a group automaton has bounded activity if there's some universal bound such that for every length n, there at most this universal bound, so C, many pairs that have non-trivial restriction, pairs of a state and a word of length n. And so with this in mind, now we can talk a little bit about dendroid automata. So this is the combinatorial model for iterated monodromy groups of entire functions that I want to use. So what is for me a dendroid automaton? So it's an automaton which satisfies the following conditions. So the first condition is that we have a dendroid set of permutations. And so here I drawn an example of a dual Moor diagram of something which will turn out to be a dendroid automaton. And so I simplified the diagram a little bit. So basically, I removed all the identity arrows and identity levels. So in theory, there should also be some gray loop like this. And whenever there's not a label, the label should be identity, but this is a bunch of noise. So we are suppressing this in this picture and from now forward. And it's not too hard to see that this is a dendroid set of permutations. Basically, I gave a proof for this particular picture in the setting of the function 1 minus z times the exponential. So this is the first condition that we want to use. And then we post some conditions on the labels. So the first condition that we want is that for every non-trivial state, we want that there's a unique pair of a state and a letter such that the original state B is the restriction of A at this letter. So in the dual Moor diagram, this means every non-trivial state appears exactly once as a label of an edge. Okay, and so here I have two, so implicitly I have two non-trivial states. I have state G and a state H, and G appears here non-trivially, appears exactly once as a label, namely for this edge, and H appears also exactly once, namely for this edge. And so the final condition I want to impose is the following. If I take a generator and I look at some finite orbit of it, then I want that there's at most one edge along this orbit, which has a non-trivial label. And if I look at an infinite orbit, then I want that all restrictions are trivial. And again, under this configuration, this is also satisfied. So we have this orbit of length 2, and it has one edge which has a non-trivial label. And so along infinite orbits, we don't have non-trivial edges. And okay, if you have an orbit of length 1, then this condition is easy to satisfy because 1 is less or equal to 1. So this is more a condition for finite orbits of non-trivial length. For example, if I would erase this h here and put this h on this edge, then we would violate the condition, because now on this non-trivial orbit we have two edges which are labeled non-trivially, and I'm also not allowed to put the edge, for example, along this edge. Okay. So I claim that I want to use this as the combinatorial model for iterated monodromy groups. So the main theorem I want to state is the following. So if you have a postlinearly finite entire function, then the iterated monodromy group is the self-similar group on an infinite alphabet, and it's generated by a dendroid automaton. And in particular, it's generated by an automaton of bounded activity growth. And here I should say it might be that we have to go to some iterate in this process of proving the result, but there's a very nice explicit version of this for the exponential family. In this case, you can easily write down the automaton based on a leading sequence. And if you're interested, I can say a little bit more about this at the end. And so how do we prove this? So for the exponential, so in general, we want to put a nice labeling on the dynamical pre-image tree. So we have to somehow identify the dynamical pre-image tree with some alphabet. And for exponential functions, here we can be very explicit and use the dynamic race landing in the posting set. And so if you want to work with general entire functions, something that we are going to use are periodic spiders. So for me, in particular in our example of the function 1 minus z times the exponential function, you have, if you take these spider legs and you look at their pre-images, you can find pre-images that are homotopic. So one pre-image of this will be this. So one pre-image of gamma 0 will be gamma 1 prime, and one pre-image of gamma 1 will be gamma 0 prime. And so there will be another pre-image landing at 0, something like this. But if you now look at this spider, you can isotope it back to this spider. and you can use this information to recover the combinatorial description with the dendroid automaton. And this is no big surprise, but so the dendroid automaton we just saw before is indeed the combinatorial description for a function 1 minus z times the exponential function. So now I want to say a little bit more about the amenability part of this main theorem. So for this, I want to take a little step back and say something about amenability. So what is an amenable group, or more general, what's an amenable action? So if you have a group acting on set X, then we call a group action amenable if there's an invariant mean on X. So this is a linear functional on the set of bounded functions on X, which satisfies the following properties. So we want it to be normalized, we want it to be positive, and we want it to be invariant by the group action. And so this is if gx on x on the left, then at x on infinity of x on the right. So this is how you write this down precisely. And we say that G is amenable if its regular action on itself is amenable. And so amenable groups are basically these groups where it's impossible to do some kind of Bernhard-Tarski paradoxon, because this would violate the properties of this invariant mean. So something I should emphasize is that we only want that this function is additively linear, so finitely additive linear. We don't say anything about countably additive. And so it's not too hard to see that finite groups are always amenable, because there you can actually use the counting measure. And abelian groups are also amenable. So for Z, you can try to do some kind of nice averaging process. You have to do some choices, but if you like ultra filters, it's not too difficult for this definition. But there are also other definitions of amenability where it's very straightforward to see that Z is amenable. And so something which is very nice about amenability is that it's closed under many group operations. Namely, it's closed under taking extensions, or taking subgroups, quotients, or also direct limits. So with this in mind, one can define a family of elementary amenable groups. So these are the groups which you can obtain from finite and abelian groups just by these operations I listed here. So this is the smallest group, family of groups that contains the finite and abelian groups and are closed under these operations. And for a long time, it wasn't clear whether all amenable groups are elementary amenable. So one of the first applications of self-similar groups via the Grieger group was to give an example of a group which is amenable but not elementary amenable. And now, so in order to deduce the amenability result for iterated monodromy groups of entire functions, I provide an amenability criterion for bounded activity automata on infinite alphabets. So for this, I have to be a little bit precise. So I want to not consider all possible permutations which are allowed, but I want to start off with a subgroup of permutations. And then I consider this group, which is the group given by automata with bounded activity, where the action of every state on the alphabet X is in P. So for every state, the first component will be contained. So for every state, the action on the alphabet will be contained in the subgroup. And so something that I'm able to prove and then apply to the case of entire functions is the following result. If you have a countably infinite set and you have an amenable subgroup of the symmetric group of this infinite set, and we suppose that the action of P on X is recurrent, then this group defined just above is amenable. And so how can we use this result in the case of entire functions? So we have to start off with a positively finite entire function with an amenable monodromy group. And so now I can also say why I have this condition that I want that the monodromy group is amenable. So in general, the monodromy group is always a quotient of the iterated monodromy group because it's the first level action. And I stated that that amenability is closed on taking quotients. So if I want that the iterated monodromy group is amenable, I need for sure that the monodromy group is amenable. And so basically the main theorem says, yeah, this is the only extra condition that you have to impose for positively finite entire functions. So if I start off now with such a function, so the first thing one should notice is that I can apply my structural theorem and work with dendroid automata. And dendroid automata have the nice property that they have bounded activity. And so that's actually not too hard to see because of the condition that every state appears exactly once as a label of an edge. So from this, you can get a uniform bound, which is just based on the size of the post-singular set. And so now, since I'm using maybe have to pass to an iterate, I have to say that the action of every state in one, the action of every state in this automaton is in the monodromy group and actually of an iterate of F. And so something which you can also check is if the monodromy group of F is amenable. This is closed under taking iterates as well. So we can suppose that we are actually using the monodromy group of F. And now for recurrency, there's a nice fact that this basically comes out of the Deutsch solution to the type problem. So we always know that the monodromy action is recurrent on the set of preimages of our base point. So we can apply this theorem. We satisfied all the conditions. And from this, we get that the iterated monodromy group is indeed amenable. So how do we prove this criterion? So for this, I use the following theorem by Reinke, and De La Salle. And so it's a bit of a mouthful, so I won't state this theorem in its sole form, but so something which I want to say is they had as their main applications groups acting on compact sets, and so I had to adjust a little bit their conditions such that it also works in the setting of infinite alphabets. So this is the change that one has to do. And so the recurrency comes into play for this condition here. And so for the other conditions, it's not too hard to see that it's satisfied in the setting of finite state automata of bounded activity with an amenable isotopy. So we can apply this theorem to the group that we have. And so the thing which is a little bit doable is to promote the recurrency of the action of X, is to promote the recurrency of the action of P on X to the action of P on the whole set X omega, which is basically the set of ends of the standard X regular tree. Okay. So with this in mind, I can a little bit say something about what's also possible in further directions. So something which you might have get a little bit of taste of, but it can be done more general, is that you can use iterated monodromy groups to take them as topological models of entire functions. And so this is one way of approaching transcendental Thurston theory from a very algebraic perspective. And if you take this in mind, then there's, from this combinatorial perspective, a very natural way of how to approximate post-singularly finite entire transcendental functions by post-singularly finite polynomials. So another thing which is a little bit more group theoretic is it's also known that if you look at linear activity automata on finite alphabets, and so I think also even quadratic activity automata on finite alphabets, then they're also always amenable. For me, it's not so clear at the moment how this should work in the infinite case. So that's an interesting direction to look at. So another thing, IMGs can be, of course, also applied in the rational case, and there are very interesting questions there. And so we can also go from transcendental and rational to meromorphic functions and try to study IMGs of meromorphic functions. And another question that was a very successful application of IMGs in the rational case is to get a combinatorial understanding of the Julia set with the help of IMGs. And I am hopeful that it's also possible to do this for transcendental functions. But so what you should be a little bit careful about is that the Julia set for transcendental functions is much larger than in the rational case. And so what you should really think of, it's more of an analogy of encoding the landing behavior of dynamic rays for polynomials to encoding the landing behavior of dynamic rays for entire functions. And so if you don't have dynamic rays, then maybe you have to use dreadlocks. And so amenability is only one group theoretic property, and I'm still interested in looking at other group theoretic properties of IMGs of entire functions. And so here again are the main two results. So the structure result that you can describe an IMG of an entire function by a general automaton, and the amenability result that the IMG of an entire transcendental function is amenable if and only if the monodromy group is amenable. And so I want to end my topic, end the main part of my talk by saying that there are still many interesting directions to continue. So thanks a lot for your attention. And so I can still go in some directions if there's interest. So there's a little bit about the, here's the bibliography for the things that I've cited. So I can talk a little bit about this polynomial approximations, about the special case of exponential functions. So there we can be very combinatorially explicit and say a little bit more about the structure of the resulting Schreier graphs. I can say a little bit about why we actually have recurrence for entire functions. And okay, this is just a reference what's the precise statement I mean by invariance bias. But I can also take this opportunity to open up for questions. Yeah.
Okay, yeah, so thank you, Bernhard. So let's thank the speaker for the nice main part of the talk, as he said. So yeah, so are there any, well, since the speaker offers some interaction and choice, so are there any particular preferences for the continuation from the audience? Or any other questions or comments? So
I have a question. What about particular groups where there's well studied? For instance, Basilica group was studied for quadratic dynamics and have many interesting properties. What about IMGs for entire functions?
So something I can say in this case is I focus a little bit more about exponential functions. So something which is known for the Basilica group is that it's amenable but not sub-exponentially amenable.
Yeah.
So here is something which is also true, is that if you have a group which has sub-exponential growth, then it's always amenable. And then you can also construct the family of groups that start off with finite abelian and groups of sub-exponential growth and do the same operations. And then you go to the class of sub exponentially elementary amenable groups. And so the Basilica group is an example of a group which is amenable but does not belong to the set. And so something I can say is also that every IMG of in the exponential family is also does not belong to the set. For the exponential family, it's it's for
Seems my connection was broken for a moment. Sorry.
Okay. What did I want to say? Okay, so for polynomial IMGs, it's always an interesting question whether they have intermediate growth or not. This is not so much an interesting question for IMGs of transcendental functions, because often enough the monodromy groups are way too large, such that you always get exponential growth just from the monodromy groups. So for example, if you look at the exponential family, then the second iterate always has the same monodromy group, and it will be always of exponential growth. So something which might be interesting is whether there's basically some notion of growth which is going higher than just exponential, okay, a bit coarser than word growth, whether you can say whether there's some infinite bigger version of growth which could be intermediate also for the transcendental case.
Okay, thank you.
Okay, thank you for your question.
Are there any other questions? Or online, maybe? No. Then I have a question actually about transcendental Thurston theory. So you have this combinatorial data given by the IMG action on the rooted tree. So actually, do you know that maybe within some families of maps, which actions are actually realized by some transcendental entire function, not like topological one? Yeah.
Are you asking about the realization problem in a specific family?
For example, or you know it in general. You can do it in general.
So I think it should be possible to do this if you already have the solution to the transcendental Thurston theorem. So I think, for example, so there's a realization result for the Thurston theory of exponential maps. So there we know that transcendental topological exponential map is realized if and only if it has no Levy obstruction. And so I think I can encode also in IMGs what Levy obstructions are in the exponential setting or in the more general setting. But so I think I would also need the in order to answer your question completely, I would need a complete answer for the transcendental first theorem. So,
and then maybe additional like stupid question. So is for this combinatorial data, can you at least say that for any type of such data we have topological transcendental interfunction which realizes it? So it's at least on this level, so that we start the Thurston iteration.
So this depends a little bit upon what you mean by topologically entire. So something. So in principle, you always can realize this as a topological map, but you have to know the solution of the type problem to know whether you can actually do Thurston iteration or not. So something I didn't emphasize here too much, but it's actually hidden under the rug. So if you want to do algebraic computations and algebraic models, what you're doing is you're not actually using directly IMGs, but you use the language of bisets. And so I decided to not talk too much about bisets here because it's a bit more algebraically. But so I think but so you should kind of think of them as labeled trigraphs. So this information also encodes the biset. I won't go into too much detail there. And so on this level, I think it's possible to give a combinatorial description of bisets that you can topologically realize as topological maps. And so this is basically where one motivation for the dendroid set of permutations come into play. And then you have to basically solve the type problem to know whether you can do Thurston iteration on the conformal structure of C without finitely many points, or whether you jump to the disk.
Okay, thank you. Thank you. Any more comments or questions by the audience? Okay, if not, then let us thank the speaker for the nice talk.
Thank you. Happy Easter.